So let us now look at how a direct mapped cache works with an example. Let us consider a cache which is initially empty. It has 8 lines or 8 blocks. It's a direct mapped cache. It has a valid bit, tag, and data. Now the processor is sending these addresses in sequence, one after the other. So this is written in decimal. The binary of that is written here. It's a 5-bit address. So the objective is to determine how many hits and misses towards the end of the address sequence. So this is a typical quiz question in almost all universities. So first thing, you have this address 10110. The first task is to split it up into tag and index. So how many bits of index? Find out how many lines are there in the cache. There are 8 lines. So you need 3 bits for index and 2 bits for tag. So firstly, you will get this address 10110. Index is 110. Go to 110. Check for the valid bit. It's not valid. Here it is written as n. N means not valid, or it is 0, which means it is a miss. So the first address is a miss. So what would you now do? The address 22 is a miss, and therefore you would go to the memory and fetch the content of 22, update the cache with the content memory of 10110. You update the tag. What was the tag? 10, and update the valid bit. Make it yes, it's valid, or make it 1. Now you can pause at this point. You can repeat it for the rest of the addresses and then check the result at the end. I'm going to do it one by one for all addresses. So next address is 26. Repeat the same process. 11010 is the binary value of the address. So remember, this is the address and not the data. So you're going to split it up into index and tag. 010 is the index. Go to 010. So this is the most updated content of the cache. So I'm going to use this. The valid bit is 0, which means it's not valid. Therefore, it is again a miss. So the first one was a miss. The second is also a miss. So address 26 is also a miss. So I'm going to place, go to the memory, fetch the data, put it here, update the tag. The tag is 11. So these two were misses. What about 22 now? You don't have to look at the cache. You can say that it is a hit because 22 had already occurred here. But how do you look up in the cache is take the address, split it up into tag and index, go to that particular index, check the valid bit, it is valid, check the tag, it is 10, match the tag to the tag of the address. If it is the same, then it means the content of 10110 is present in this location. So basically it is present, therefore it is a hit. Repeat that same thing for 26. You will see that you will end up here and you will see that it is a hit. Now let us see what happens with 16. 16 is 10000, so it is index is 0. You will go to 0, you will not find the data, therefore it is a miss. And you fetch the data from the memory, put it here in the cache, update the tag. The tag is 10. Next address is 3, 00011. Again, it's a new line. So if you look at this, it's a new line. There is no, it's not valid, it's an empty line, and therefore it will be a miss again. And therefore you bring the data, put it in the cache, update the tag. The tag is 00. Now let us see what happens if you get 16 again. 16 again, you can look at the sequence again and see 16 was already referenced. So that is the whole point of a cache. Whatever was recently referenced to, you want to bring it into the cache. That's why we have a cache. So 16 is going to be a hit because 10000, let us go back to the previous slide. 10000, index is 0. You find the valid bit, it's valid. Look up the tag, it matches with this address sent by the processor, and therefore the data is present, and therefore it's a hit. Now let us look at the interesting part of 18. What happens when you get 18? You can maybe stop at this point, do it on your own and compare the result. You get 10010. That's the address for 18. So it is 10010. We are right now at this point. So you go to 010 and you try to do a tag match. You match the tag from this address to the tag present there. You will see that the tag doesn't match because it is 10 from the address in the processor and the tag present in the cache is 11. Therefore, there's no tag match and therefore it is a miss. So now at this point, can you tell me what is the uh, address, what was the address referenced to here? How do you find out from the tag what was the data present here? It's quite simple. You take the tag, concatenate it with the index. So the tag is 11, you concatenate it with the index, so 010. So basically you have the memory of 11010. So the data present in 11010 is present here. But what you want is the data of 10010. So therefore what you're going to do, this is a miss for sure. So you're going to go to the memory, fetch the data, and then put it in that same location. You have only one location. You cannot put it in any other index. You have to place it in that particular index. So you're going to delete this data or evict that data, and you're going to replace it with the data of 10010. So that's what you've done here. Update the tag. And lastly, you get 16 again. It's going to be a hit because if you go to 10000, you will find the data for 16. So overall, now if you summarize, I forgot to keep track which one were misses, which one were hits. You can take a look at this. I think this is right. So you can count how many misses out of, there are about 9. Out of 9, how many were misses and how many were hits. And that is going to give you the miss ratio and the hit ratio. So now let us move on to another interesting concept of the block size before we wrap up the direct mapped caches. So earlier I said that we can have one block of data, which is 4 bytes in the cache. Now, is that the maximum size of the block? Can I increase the size of the block? So what I can do is I can fetch 4 words at a time. Instead of fetching one word, which is of 4 bytes, let's say I decide to fetch 4 words at a time, which is 16 bytes. So this is one word, second word, third, and the fourth word. And each of this is 32 bits wide, or each of this is 4 bytes wide. So what is the advantage of this? Basically, if you have spatial locality, if you are always referencing A of 0, A of 1, A of 2, etc., if you fetch a lot of data and put it in the cache, you're going to increase the hit rate because you don't have to go to the memory and come back. That is the advantage. We will see the disadvantage later. So now first let us see how do you address this cache. So now how many bytes are there in this line? You have 16 bytes. And let's say I want to allow byte access. So how many bits do you need to access 16 bytes? So I want to reference each byte at a time. So this is byte 1, 2, 3, 4. Let's say start from 0. Byte 0, byte 4, up to byte 15. So how many bits do I need for this byte offset? Clearly, I need 4 bits. This is 0000 up to 1111. And therefore, earlier, remember, we did what is called as a byte offset. So we will need, instead of, we had done 2 bits earlier, now we will need 4 bits of byte offset to reference to each of these bytes individually. And then we will need an index, which is 2 bits because there are 4 lines. And then the rest of them are tag bits. Now there is also another way of looking at this. Instead of referencing to the entire 16 bytes, we can look at it slightly differently. So this is block 0, block 1, block 2, and block 3. So basically 4 blocks. So I can split this. So instead of referencing it as 4 bytes, I can split this up as 2 and 2. And I can call this as block offset, which means this is block 0, block 1, block 2. So 1, 0 basically means I am currently in this block. And within that block, I would refer to the 0th byte. So each block will contain 4 bytes. So we looked at this example, 4, 2, 1, 2, 3, 4, 5, 6. So each block is going to contain 4 bytes of information. So if I, in this block, currently I'm in this block, and here I want to use the 0th byte. So basically this was 01, this was 00, this was 01, this is 10, and this is 11. So in either case, so even if you, whether you follow this method of a single 4-bit byte offset, or you take a look at this as separate block offset and byte offset, you will still end up with the same data. So you can try it out with an example. Some of the books use this concept, some of the books use the other concept. That's why I've told both of them. So for simplicity, we can just stick to this concept of just 1 byte offset. But in either case, you will end up with the same data. So to summarize, what is the advantage of larger size blocks? So one is you have the same tag. So remember, you have the same tag bits for the entire block. So for the entire 16 bytes, you have the same tag bits. So that's important. So the tag is the same. You take advantage of spatial locality, like I said, therefore lesser miss rate. But actually, if you run an experiment of increasing block size versus miss rate, you will see that miss rate drops, but later it increases. Why does it increase? Because there is lesser data stored in this cache. So what will happen is, if I have data, a cache which is of 16 lines, now I want to convert this into increased block size. So what I will typically do is reduce the number of lines in the cache and increase the size of the block. Okay, so instead of 16 lines, what I'll do is I'll have just 4 lines and then increase the size of the block. Okay, so this way what will happen is the overall size of this cache will reduce because the number of lines have reduced. And therefore you will see that the miss rate increases. So if we will actually run this experiment and you will understand it better. So lastly, to summarize, how do you figure out what is the size of a cache? So I've written some formulae here. You can take a look at it, but I'll tell you a simple way of finding out the size of the cache. Just look at the cache. How many lines does it have? 1024. How much of data is there in each line? So forget the tag and the index. That also occupies space, but we don't count it as the size of the cache because it's not containing any valid data. So what is the size of the data here? It's saying 32 bits, or in other words, 4 bytes. So this is going to be 4 kilobytes. So capital B is bytes. 4 kilobytes is the size of the cache. So if this was 64, then it would be 8 bytes. So you would accordingly figure out the size of the cache. So you can also have some formulae and figure out, but I think this is a much easier way of finding out the cache size. So that's all I have for direct mapped cache. In the next lecture, we will look at set associative and fully associative caches.